What does the architecture of a general-purpose AI agent actually look like? One that can handle arbitrary open-ended tasks. The answer is a coding agent plus a file system. We'll walk through how that coding agent is built, how it's kept safe and reliable, and then how code generation becomes something much bigger than writing programs. A meta capability that lets an agent create new tools, rules, media, interfaces, and even new agents. Successful general-purpose agents converge on the same pattern: a small set of general tools for code execution, file read and write, and search, with capability modules like browsing layered on top. Why does code carry so much weight? Because it forces precision. Age greater than 18 and identity verified is ambiguous in plain English, but written as code, it means exactly one thing, and code that runs is its own proof of correctness, something natural language can never offer. Take a simple task. Organize leftover TOD comments and file issues by priority. To do that, you need to browse directories, read code, edit files, run commands, and search for patterns. Those 5 operation types map onto 7 core tools: a code interpreter, a bash shell, and tools to read, write, edit, glob, and grep. Simple individually, but together they cover a remarkable range of tasks. It's a minimal toolbox almost any agent framework can adopt cheaply. Here's what that looks like end to end. The agent searches with grep, finds 3 matches, and writes them to a file. 2 tools, task complete. If the ask were more complex, like counting TODs per module and charting them, the agent would reach for a code interpreter to run the statistics and the plot. Simple tools, combined intelligently, cover a lot of ground. Why is coding the core, rather than research or computer use capabilities? Because nearly everything else reduces to code. A PowerPoint file is just structured markup. A data report is generated code. Even successful GUI interactions can be recorded and replayed as automation code. Wherever direct code or API access is available, it beats simulating mouse clicks. Cheaper, faster, and far more reliable. Walk through a realistic flow, analyze last quarter's sales data, and create a summary report. The agent starts by reading its memory file, discovers the user's preferences and data source, pulls the data, writes and runs an analysis script, produces the report, and writes back what it learned so it doesn't have to ask again next time. Notice, the file system touches every step. It's the hub of the whole operation. A surprising design choice. Long-term memory is stored as plain markdown files, not embeddings in a vector database. That turns out to be powerful. Users can literally open the file and edit or delete what the agent remembers. The format preserves time order naturally, and it's version controlled like any other file. Because the agent can write files, it also has a way to durably record discoveries. Like learning a bank requires a branch address for verification, for next time. This isn't a universal law. It applies specifically to open-ended, general-purpose agents where you can't enumerate every tool in advance. A narrow customer service bot, by contrast, has a closed task space. Its core is built around fixed processes and domain tools, and code becomes just one tool among many, like policy verification, rather than the architecture itself. Even there, though, coding remains a baseline capability for precise calculation and rule checking. Some agents are sessionless. You message them like a person, anytime, with no app to open and no login step. The engineering challenge behind that simplicity is preserving state across messages that might be minutes or days apart. Installed packages, working directory, background processes. The solution splits state into 2 layers. Files persist automatically, while process state is kept alive during active use, serialized to disk before being torn down and rebuilt on the next message. An agent that can read files, execute commands, and reach the network is powerful and dangerous once compromised. The lethal triad names the pattern: access to private data, exposure to untrusted content, and the ability to communicate externally. Together, they form a complete attack loop. Malicious instructions hidden in a web page or email can trigger the agent to read private data and exfiltrate it. Persistent memory makes it worse. An attacker's instructions can lie dormant across sessions and fire later. A sandbox isn't a switch, it's a series of decisions. The single most important one is network egress, no access by default, with a whitelist proxy for the few destinations a task actually needs. Even if malicious code runs inside the sandbox and reads sensitive data, with no way out, it can't exfiltrate anything. Combine that with read-only source mounts, a writable workspace for outputs only, and never mounting credentials. Invisible data can't be leaked. You can't stop shell attacks with a blacklist of dangerous words. A delete command can be smuggled in through a seemingly harmless file search command, or reconstructed through variable expansion. Production systems parse commands semantically to understand what they actually do, not just what they look like on the surface. And to keep this fast for users, the check runs in the background while the interface shows a harmless progress hint, very different from speculative execution in a processor, since there's no real state to roll back if the check fails. Here's a subtler risk. Whose side is the agent actually on? An agent negotiating a price on your behalf isn't talking to a user who needs help. It's talking to an opponent. Models default to helping whoever's speaking, which is dangerous. The failure modes sit on a seesaw. Too honest, and it leaks your bottom line under pressure. Too suspicious, and it can't get its own job done. The fix is an explicit loyalty policy. Protect the principal's information, resist pressure, and never over-explain a refusal in a way that leaks the very thing being protected. For high-risk operations, the agent is probably loyal, isn't good enough. Enforcement has to move down to the data layer itself. The idea: every data object carries its own permission rules and validators in a schema that humans reviewed, and every write is checked against it, with the agent treated as a restricted principal rather than trusted code. In trials, this approach let through zero rule violating writes, versus a meaningful number for every softer approach, for about 2 extra milliseconds per write. Here's the ideal engineering workflow: trimmed down for simple tasks and run in full for complex, high-stakes ones. It starts with reviewing project documentation, then clarifying requirements, writing a design document for approval, implementing code with a test fix loop, running a self-code review, and finally syncing documentation. One detail worth remembering: defining done as tests pass rather than code written is what turns a code generator into a reliable engineering assistant. Coding tasks are especially well suited to rigorous engineering because they naturally sit in the best possible position. Clear goals, automatically verifiable results. Test suites define done. Linters give instant feedback, and version control gives near-perfect rollback. That's not because coding models are unusually powerful. It's because decades of software engineering infrastructure hand this discipline a robust foundation for free. 3 real-world proof points. A large-scale code migration succeeded by encoding knowledge and constraints into linters and continuous integration, rather than relying purely on model strength. One team improved benchmark performance purely by tuning prompts, tool middleware, and self-verification loops, and pioneered using an agent to analyze its own failures to improve itself. And splitting long tasks across an initialization role and an execution role prevents an agent from overreaching or declaring victory too early. 4 principles generalize well beyond coding. Encode rules as enforceable constraints rather than mere suggestions. Automate verification since manual review doesn't scale. Make feedback as fast and specific as possible. and make rollback reliable so bold experimentation stays safe. And there's a deeper point. Constraints need to govern how a task is done, not just whether the end result looks correct. Deleting and rebuilding a database does technically fix an error, but the data is gone. Dedicated checks on destructive shortcuts matter because a correct-looking outcome achieved the wrong way is still a failure. Before you can recover from failures, you need to classify them. Failures show up at 4 distinct layers. Infrastructure noise like rate limits and timeouts, tool misuse like hallucinated calls, context corruption like window overflow, and control flow problems like infinite loops or cascading failures. The first question is never, should we retry? It's, would retrying even help? Because retryable and non-retryable errors need completely different handling. Recovery escalates in visibility. Try silently first, then degrade gracefully by adjusting the request, and only surface an error to the user once every automatic option is exhausted. But recovery mechanisms can themselves fail, so every path needs a hard ceiling. One real example: a compaction circuit breaker trips after 3 consecutive failures. A threshold pulled directly from production data after one session failed on this exact path over 3,000 times in a row. 5 techniques close the gap between an ideal workflow and a fast, responsive system. Tool calls run in parallel and start executing as soon as their parameters validate. Files are read in ranges with line numbers attached, so edits stay unambiguous. A live status line injects the current branch and pending changes. A persistent terminal session preserves working directory and environment variables across commands. And every file write triggers an immediate syntax check, like an editor flagging an error the instant you make it. 4 complementary search methods, typically chained coarse to fine, semantic search to find the right area of a codebase, exact pattern matching to pinpoint specific lines, and symbol lookup to trace a call chain precisely by distinguishing a definition from a reference. There's a real split in practice. Some tools deliberately skip building semantic indexes, relying purely on live text search to avoid staleness and data exposure, while others invest in indexes for cross-file semantic recall. It's a genuine trade-off, not a settled question. Editing is fundamentally about telling a system precisely what changed. One common approach replaces an exact block of old text with new text, predictable and unambiguous, though verbose for large deletions. Another approach trains a dedicated fast apply model to merge a rough diff into the full file, trading complexity for speed. For most systems, simple text replacement is the safest starting point, and matching only the start and end of a block is the best upgrade for large edits. Now, the pivot, code generation, isn't just for writing programs. It's a meta capability, an ability that creates other abilities. There are 6 applications worth tracing, moving from the inside out, from how a system thinks, to the rules it enforces, to what it presents, to the systems it connects, the interfaces it builds, and finally, to creating other systems like itself. Language models are strong at language, but weak at precise calculation and logic. The fix is division of labor. Let the model understand a problem and translate it into code, and let a code interpreter compute the exact answer. This mirrors an old insight from symbolic computation. Systems that could compute precisely used to understand language poorly, and language models fill exactly that gap. Notably, the gain from this approach is largest on weaker models. A strong enough reasoning model may not need the crutch at all. Business rules described only in prose are full of loopholes. Does refundable within 7 days mean calendar days or business days? The strongest pattern layers 3 defenses. Natural language for explaining policy to users, a checklist built into a tool's parameters that nudges careful verification before acting, and, critically, server-side validation against real, authoritative data that never trusts self-reported claims. That last layer matters because reasoning can go wrong, and some actions, like cancelling an order or transferring funds, may not be undoable. Reframing slide or video generation as code generation sidesteps the need to click around a graphical interface. But writing code doesn't guarantee it renders well. Text can overflow, images can be miscropped. The fix is a two-role loop. One role writes the code, another actually looks at the rendered result using a vision model and gives specific, actionable feedback, and the cycle repeats until quality is met. Splitting the roles matters for efficiency. One role only holds the latest rendered image, the other only accumulates short text feedback, avoiding a pileup of images from every round. When there's no software development kit, and interfaces are messy or undocumented, a system can generate its own adapter on the fly, build the client, handle authentication, pass the response, and translate it downstream. Taken to the extreme, this even applies to systems with no programmatic interface at all. Operate a graphical interface once, then capture that sequence as fast, reliable automation code for next time. The same idea powers self-healing log parsers that adapt automatically as formats evolve, without a human ever touching the parsing code. Letting a system generate raw web code to execute directly in a browser is a real security risk. It can be exploited the same way a malicious script injection is. A safer pattern has the system emit a structured description of the interface it wants, which a trusted renderer builds from a pre-approved set of components, like ordering off a menu instead of stepping into the kitchen. This also changes what a finished deliverable looks like. Interactive reports instead of static text, dynamic forms instead of 10 rounds of back and forth questions, and for databases, a query that executes directly so thousands of rows never have to pass through a language model at all. The ultimate extension of this meta capability, a system that can repair or create other systems like itself. Self-repair tools handle common issues deterministically and fall back to deeper analysis for harder, long-tail problems. But building a whole new autonomous system from scratch is much harder than ordinary application code. Naive attempts tend to reproduce the same architectural mistakes, like ad hoc state management or outdated technology choices. The most reliable fix isn't a longer set of instructions. It's starting from a known good implementation and adapting it, much like biological replication with mutation. The core idea running through all of this: code is not just a tool for producing programs, it's a language for rigorous thinking and precise expression. That's true at the foundational level, where decades of engineering discipline make these systems unusually mature, and it's true at the meta-capability level, where code becomes the mechanism by which a system expands its own abilities, including, ultimately, the ability to build other systems. A few open questions worth sitting with. How do you balance sandbox security against capability without crippling what a system can do? Can errors compound across generations when systems start building other systems? And how would you prevent that kind of drift? How should a system tell an intentional format change apart from a bug it's quietly papering over? And how do you keep automated review aligned with what real users actually want, rather than converging on the reviewer's own aesthetic?